the universe, there is an incredible variety of stars. But what happens when one of those stars die? Some turn into white dwarfs, some turn into black holes, but what about the stars that don't quite cut it to become a black hole? Well, first it's important to understand how stars actually work. They're held together by two elementary forces, the inward force of gravity and the outward force of radiation. Stars live out their life by fusing hydrogen into heavier elements radiating out energy. First, it fuses hydrogen into helium, and from helium all the way up to iron, which can no longer undergo fusion. As iron begins to build up in the core of the star begins to wither and die. Once the star has exhausted all of its fuel, the outward force of radiation begins to lose out to gravity, and something very odd happens at the center of the star. If the mass of this star is roughly 8 times the size of our sun, the outer part of the core begins to collapse catastrophically. As the core of the star itself rushes inward at roughly 70,000 kilometers per hour, the physics of nuclear structure begin to break down under the intense gravity. Electrons are forced inward towards the center of atoms in the core, fusing with protons to create more neutrons. Each atom is now made entirely of neutrons. As the outer portions of the star fly out into space, something very dense and very tiny remains: a neutron star. This neutron star has a mass of roughly 3 times that of our own sun, but it has been pushed into a point roughly 25 kilometers in diameter. Now let's cut this behemoth open. On the very edge of a neutron star, there exists about 10 centimeters of plasma, heated roughly to 1 million degrees Kelvin. For comparison, the surface of our own sun is just under 6,000 Kelvin. As we move toward the core, we pass through the star's crust. The crust consists mainly of a lattice packed with iron atoms, with electrons flowing freely from atom to atom. Deeper still, we reach the outer core, which is where things start to get a little strange. As even the most basic chemistry student knows, an atom consists of protons, neutrons, and electrons, which, arranged in different ratios, produce the elements we know and love. But with atoms packed so densely, the positively charged protons and the negatively charged electrons repel one another, forcing them out of the outer core, leaving only a dense soup of neutrons, known formally as neutronium. With a total proton count of 0, it resides at atomic number 0 on the periodic table. However, a sample of neutronium the size of a die would weigh about 1 billion tons, more than Mount Everest, and would be so dense that to it, the Earth would be nothing more than a slightly dilute vacuum, as it easily falls through any possible obstacle. Now on to the core. The core of neutron stars tend to get a little confusing. No one really has any idea what goes on in here, but there are a number of educated guesses. The leading theory is that behind the lattice of neutronium in the very center of the star, there exists a quark-gluon plasma soup. To learn precisely what this is, we have to learn a little bit about what quarks are. Quarks are the stuff that make up atoms. Protons, neutrons, and electrons are not composite particles and are actually built using different series of quarks. It's impossible for scientists to separate neutrons into individual quarks for a number of super-duper complicated reasons. However, at the center of these high-mass neutron stars, the density and temperature is just enough to easily separate these quarks from one another, allowing them to flow around lacking any material structure. Now that we know the structure of a neutron star, there are plenty of strange qualities to be explored on the outside. Neutron stars, with their immense energy and density, tend to spin very, very violently. So violently, in fact, that neutron stars can spin up to 25% the speed of light. This is so fast that neutron stars often lose their spherical shape, becoming oblong and oval. This causes the magnetic fields of neutron stars to be so strong that when an object enters its influence, the magnetic field alone is enough to bend the individual atoms as it emits a radio signal. Stars spinning this fast with this density emit an incredibly strong radio signal, giving certain ones the name of a pulsar. This radio signal from most corners of our galaxy can be picked up by complex equipment back here at home, which originally allowed for its identification. Well, a little more complex than that. Did you enjoy this episode? Put a like down there and subscribe to see more. Have you got a question you'd like to see answered? Put it in the comments and we'll be happy to create a video.